Welcome back. Another day, another dollop of misery on this website, LeetCode. I don't know if it's day 8 or day 9, but feeling like I'm getting into the groove. I feel like I'm really getting into the groove with this LeetCode stick. I had to check something real quick. I feel like I'm really getting into the groove with this LeetCode stick. The days I'm practicing are getting a little longer, but it's a feel strong, man. End game, ideally, having every LeetCode problem done would be so hype. That would be so hype. That would be actually amazing. Or being able to speedrun all the problems, maybe like a 24-hour stream or something. That would be really hype. And then yeah, I guess I would just never do it again. I don't know. But back once again. The grind does not stop. I wonder if there's anyone who's ever finished all the problems. That would be pretty hype though. I don't think anyone has ever sped-run all the problems, so that would also be pretty hype. But got some problems today. Looks like we're going to start with the square root of x. 20 minutes on the clock as usual. By the way, go ahead and join the Discord, the hyperbolic coding chamber. I mean, yesterday we started at 0 people. It's at like 100, 150 right now. So it's going crazy. There's no one in there. It's just me, actually. It's just me in there right now, but we're going to get a lot more people in there. I feel like there's a lot of people on the LeetCode grind, but soon we'll have one place, the daily LeetCode grind. But I think that's all that's on my mind. I think we did valid anagram yesterday, or there was a few more that we did the other day. I kind of want to do some new problems, to be honest. And maybe I'll queue some up, because I think we might actually get to some today. But give me 1 second. I've returned. I found this little cool link on LeetCode called the LeetCode 75. That seems pretty cool. So, might do this, might not. But I feel like I'm getting distracted. I got to focus on doing all my problems due today first. And then we'll do some LC 75. But let's just jump into it. I'll put 20 on the clock and just get into it. Square root of x. I can already visualize this. We can do this in log n. So we have a function, my square root. We're passing in a singular number and returning a number. So given a non-negative integer x, non-negative means positive only. Compute and return the square root of x. Since the return type is an integer, decimal digits are truncated. There's no integers in JavaScript. Only the integer part of the result is returned. Note, you are not allowed to use any built-in exponent function or operator such as pow or x to the 0.5. Interesting. So the square root is the number such that 2 squared, 3 squared, it's basically a squared equals x. But since the return type is truncated, they basically only want the integer. So for example, the number between the square root, if we do the square root of 2, we get 4. I mean, if we square 2, we get 4. If we square 3, we get 9. So 4 and 9, 8 is between 4 and 9. The actual answer for this is 2.82842, but they want us to only return the whole number. So that makes sense. So how do we go about doing this? Well, we can phrase the problem as a binary search over an ordered search space, and the search space would just be the set of all positive whole numbers. And so what that looks like is we're going to go with 2 since we're trying to find the square root. So our base number is going to be 2. I mean, yeah, the number that we're squaring is always going to be 2 since we're squaring. We're just going to keep swapping out, 1 squared, 2 squared, 3 squared, so on until we equal x or we pass x, right? So binary search over a, right? And a is that whole number we mentioned earlier. So how do we do a binary search? Well, we're going to use this version, which starts with the 2 ranges. The left side is going to start at 0, and our right side is just going to be x. Even though we could safely do x over 2, let's just do x This version is going to be while left is less than or equal to right. Right, we're going to calculate our pivot, right? And our pivot's going to allow us to have the search space on each iteration. That's going to be left plus the math.floor of right minus left over 2, right? And that's going to give us our pivot, and our pivot is actually going to be our base number, right? So imagine we're searching for this number like 8 or something. You know, our range is going to be 0 going to 8. We calculate our pivot, it's going to be 8 minus 0 is 8 over 2 is 4, right? 4, right? So we're going to do pivot squared, right? Does pivot squared equals x equal x? 4 squared does not equal 8, right? So what does that mean? It means that we just, oh, well, actually, have this in reverse. Pivot, if pivot squared equals x, right, then that's great, right? We found the square root of x, right? So we want to return that, which is going to be pivot. Otherwise, you have to check if pivot squared is greater than x, right? Well, if it's greater than x, which it is, right? 4 squared is 16, which is greater than x, which is 8. What do we want to do? We want to have our search space. So the right side of our range is going to be left and right up here. Is now going to be pivot minus 1. And then we can actually duplicate this right here. And the reason we're going to duplicate it is because it's going to be very similar for when the pivot squared is less than x. So let's reverse it, right? Let's just say that we're searching for the square root of 8. It's kind of hard. Let's just say we're searching for the square root of 36, which is going to be 6, right? So we're searching for the square root of 36, right? And let's just say by any means, by any reason or some form of convenience or coincidence, our current pivot value is like 4. Well, if we do 4 squared, right, that's 16, which is less than x, which is 36. If that's the case, then everything before 4 should also be zeroed out, right? We shouldn't even consider it because 4 is already too small, which means 3 squared, 2 squared, and 1 squared are also already too small. So the inverse of that operation for the left range is going to be pivot plus 1, and we're adding 1 in the case of left because left is incrementing towards the center, and right is minus 1 because we're incrementing towards the center. Both, we're adding 1 and subtracting 1 because in both cases we've already processed the pivot up here, and so we don't want to reprocess it, right? And so this leaves us with 2 cases, right? Either we're searching over our search space and you know, the pivot squared actually equals x. In that case, we return the pivot. That's great. In the other case, though, what do we end up with, right? We end up with this loop, right, ends when both ranges pass each other, right? In that case, right, what have we done? So the best way to explain this is, let's just say we're looking for x equals 4, and we're trying to find the square root of 4, which is 2, right? We go through the motions, we calculate our pivot. What we find is that 2 squared does indeed equal 4, right? That's this exit case right here, this return. Right? When we do something like 8, right, there's never a case where we exit through this line of code right here, right? Because we're only working with whole numbers here, and the square root of 8 is not a whole number. So the only way we're exiting that one is by them passing each other. So either left passes right or right passes left. Either way, if one of those happens, it's the same. In that case, what do we do? In that case, right, the number we actually end up with is 1 past where we'd like to be. The loop ends when they pass each other, so left, right? When they pass each other, left is going to equal 3. Or is it right that's going to equal 3? I think it depends. I think it's right that's going to equal 3. I don't want to guess, so we can just run it in our heads real quick. Let's do something small like the square root of 5. So the square root of 5 is going to be between 2 and 3, right? Because 2 squared is 4 and 3 squared is 9. And so it's going to be somewhere in between there. And our range is going to start at 0 and between 0 and 5. So we're going to calculate our pivot. 5 minus 0 is 5 over 2 is 2.5. Floor is 2. So our pivot is 2. Is 2 squared equal to 5? Nope. Is 2 squared, which is 4, greater than 5? Nope. 2 squared less than 5? Yes. So left gets set to pivot plus 1, which is going to equal 3. So left equals 3 and right equals 5. So we go back to the top. Is 3 less than 5? It is. 5 minus 3 is 2. Over 2 is 1. Plus left, which is 3. We get pivot equals 4. Well, 4 squared does not equal 5. 4 squared is greater than 5. So right is going to equal to pivot minus 1. Pivot is 5. No, pivot is 4. So right is going to equal 3. So now both pivots are equal to the same value, 3. So we're going to say, is 3 equal to 3? Yes. So let's calculate our pivot, right? 3 minus 3 over here is going to be 0. Over 2 is 0. Plus 3 is 3. 3 squared equals 9. It's not equal to 5. 3 squared equals 9, which is greater than 5, right? So now our pivot is going to be pivot minus, our right is going to be pivot minus 1. So right is now going to be 2, right? Which means right's going to be 2, right? That means they would have passed each other because left is equal to 3 and right is equal to 2, right? So they've passed each other, the loop would end. If that's the case, we actually want to return, I think you can either return right without subtracting 1, or you can return left, but you have to subtract 1. So we can check, if we run this code, I think I just confused them. I think, yeah, if you can, either you can return right without subtracting 1, or you can return left and you have to subtract 1. So we're good here, and I think you can also return left, but you have to subtract 1. So there we go. So yes, that's probably something good to keep in mind with this version of the binary search, that right actually passes. But I'm curious why that is. What if we swapped these right here? Oh no, this should still be the same. This should still be the same. The reason we actually can return, the reason we don't have to subtract 1 from right is because our binary search is going to be left leaning because we're flooring it. Because we're flooring our pivot, whenever we end up with 2.5 or 3.5 or 8.5, we choose the smaller one, which means we're technically always one step further left, which means that right is more likely, or right is going to pass left and be when the loop ends. I think if that's true, if I change this to seal, you can return left by itself, but you have to subtract 1 from right. So this should fail. Oh. 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 Let me run. Wait, that makes no sense. Okay. Interesting. So is it always right that's going to pass left and end the loop? That's kind of strange. I wonder why that is. You know, it could just, oh no. Oh my god, what am I saying? I'm not even triggering this case because 2 squared is 4. We're always exiting through here. I could still be right. So if I do left minus 1, right, it should work on the first case because we're exiting through line 8. If I submit, this should fail. Oh, okay, I don't know what I'm talking about. But for some reason, I guess right always passes left first in this binary search. So that's interesting. So we're converting a sorted array to a binary search tree. Given an integer array nums where the elements are sorted in ascending order, so we have an array of numbers here, the elements are sorted in ascending order, converted to a height balanced binary tree. This just means that we choose the center every time. This just means that we choose the center as our pivot every time. A height balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than 1. Okay. All right, so there's an example 2 here. If we convert the number to a binary search tree, there's actually 2 answers. This is because to create this binary search tree, in-order traversal of a binary search tree is actually not unique, right? Because you can either be left-leaning or right-leaning. So that is why there are multiple accepted answers. And even these, you can see left or right-leaning. So we're converting a sorted array to a binary search tree. Interesting. Sorted array to a binary search tree. The elements are sorted in ascending order, but also in order traversal of a binary search tree. In order traversal of a binary search tree produces an array in ascending order, which means if we already have an array in ascending order, we just have to use in order traversal to create the binary search tree. If that's the case, then we can we have to return a binary. Okay, well, if that's the case, we have to create the binary search tree from the array. Then we can just return this helper function. And what we're going to do is do a recursive binary search. And then actually we'll try and do it iteratively after this. We'll do a return helper. And we're going to pass in the range for a binary search. It's going to look a lot like square root of x, right? We're going to go, except in the array, we only want to work on the numbers that actually exist. So in the binary search earlier, I passed in x, right? You can see it here. Well, it's gone, but I passed in x, right? But in the array, we're actually going to be exclusive of the last index because it actually isn't a value. That's the end of the array. We're going to pass in nums and we're going to return a tree node or null, right? So in order traversal is just L and R, right? So how would you go about converting this array of numbers to a binary search tree? Well, we could do a binary search over the array on each iteration. On each recurse, as we're recursing through, we can build the nodes. All right, see, now I'm having a transference issue from yesterday, or interference. But for this one, we'll just make sure that left is less than or equal to right, which means the node right hasn't passed left yet. And if it has, we're going to return null, right? It means it's not a valid node. If it hasn't yet, right, then we'll calculate our pivot, right, which is going to be the same as what we just wrote in our last problem. So we right minus left over 2, right? So we're going to create a node, a tree node. And what we're doing here is we calculated the pivot, right? So now we're going to insert that node into, since we calculated our pivot, we're going to take that pivot value we calculated, sub it into the array, and then create the tree node. So we calculate the midpoint's going to be 0 here. We're going to create a node. It's going to have the number 0 in it over here. And then for the left and right subtrees, we can just recurse for their values. So node.left is going to equal helper going from left to pivot -1, passing it num so we can access those values. Duplicate this line, we'll do node.right. We're going to go from pivot +1 right to right. And so basically binary search just serves as an environment for us to split our ranges into smaller and smaller ranges. And then as we calculate our pivots, we place values into the tree node. And then we can return the node. So I think this is fine. Calculate the pivot, right, ref plus math dot flow of right minus left over 2. That looks good. We're going to create the node and then sub our value of the pivot into it. Then we have node.left, and then we're going to call a helper of left going from left to pivot -1. We already processed pivot, so we want to subtract 1. Go to nums, and then we want to work on the second range because we already set up pivot with the node value here. Node pivot +1 to right. Whenever we don't have a valid value, we're going to return null for the leaves that are dead. Okay, that looks good. The time and the space complexity, I'm going to keep it a buck. I have no idea. I know that we have to visit every node. We have to visit every every number in the array. Since we have to visit every number in the array, it's going to be at least linear time. The space complexity, however, I'm just not a space complexity guy. I have no idea. The space complexity, going to be log of n. It should be log of n, I think, just because of the recursion. But also the binary tree. Binary search log n. It's actually not log n. Part of me wants to say I feel like this is one of the ones where the height is the number of the space complexity, which is going to be tied to the recursion, is, I want to say, I don't want to guess though, I feel like it's either log of n but that also doesn't make sense. It depends on how deep we recurse. Yeah, I think I just need to do more recursive problems to understand what's going on. Like the space part just doesn't make sense to me. Recursion stack requires log of n space because the tree is height balanced. Oh, I see. Is the height of the tree correlated with how many recursive calls we do? In the worst case, I guess that's what they're saying. In the worst case, we take up this amount of space because we have to recurse that deep. O log of n space because the tree is height balanced. Since it's height balanced, it's going to be log of n. So something about the height and the tree, something about the height of the tree is tied to space. Keep that association in mind. Let's try and do this iteratively. So convert this array into a binary search tree. Since the array is already sorted, my brain is fried. Since the array is already sorted, it saves us a bit of work. We just have to convert it into a binary search tree. We just have to convert it into a binary tree, I guess. If we use in-order traversal, which would be LNR, we wrote one similar to this yesterday, and you do this with the stack so that you can keep track of where you are, keep track of your recursion, how deep you're recursing, and making sure you can backtrack to the correct nodes. That being the case, we're going to need a value which we're going to set to, this is interesting. When I wrote it yesterday, we were recursing through an already built binary search tree. This one isn't built yet, so does that mean I would just create it? Or maybe I would swap it. For the algorithm yesterday, it was while cur wasn't null, you go to the next node and so on and so forth. I think you still need a stack. I guess you can just do new stack like this in JavaScript, but also an array is the same thing. If you only operate at the end, I mean. So I think I know how we would do this. Before, we were using the main root node as a sentinel to control the loop. We duplicated it on the inside by continuing to go left. This is how we enforce LNR. Maybe a version of this would be to do this, but with the array. So we actually, maybe the goal would be to first have a basic pivot, which would just be 0, plus the math.floor right minus left, which is 0. So it really would just be nums.length over 2 math.floor of that. So we could say while pivot equals while pivot is greater than or equal to 0 and pivot less than or equal to nums dot length minus 1, and then we'll do or. I'm just going to use an array for this for now because I don't know the API for this. Or the stack isn't empty, then we want to keep going with our loop. I'll make this a little smaller, right? So while we have a valid pivot and our stack isn't empty, then we want to keep going. Then we want another one. This is how we did it for the binary search tree, and I think you can mimic it. There's something fuzzy about how this all works together. I need to read like a tree book or something. And so we're going to want to calculate our pivot here, which is going to be and we will do stack.push current pivot, right? And then we're going to use this to go as far left as we can go. Pivot equal math.floor of right minus. Oh, this is so different because right and left change. Actually, no, it doesn't matter. Right and left don't really change, actually. Left and right, basically. At least for this, in this case, we don't really care about left and right. All we care about is the pivot. So right is actually going to be, right is always going to be nums.length minus 1, and left is always going to be 0. And I know left is 0, always going to be adding 0, but it just helps me conceptualize the problem. Right minus left over 2. Okay, we calculated a pivot. Okay, so how would you go left in a binary search? You would typically go left by shrinking the pivot range. It equals left plus math.floor. Left plus math.floor, right minus left over 2. Stack.push pivot. This doesn't make sense. Left and right have to change, otherwise the pivot I'll calculate will always be in the center. Maybe I should push onto the stack a tuple. Oh no, maybe it only needs to be a tuple, since based on the tuple we calculate the pivot. So what we actually push on the stack is a tuple of left and right. And then we'd want to go left. How do you typically go left? You typically go left in a binary search by doing right equals pivot minus 1. We actually don't have to do it like this. We can just keep going while left is less than or equal to right. I think it's coming to me. It's less than or equal to right, and the stack isn't empty. Then we'll keep going right. Once we can't go right anymore, once we can't go right anymore. Damn, this is a tough one. Doing this iteratively, it's like really strange. Oh man, I might not have enough drip for this. Right equals pivot minus 1. Pivot equals left plus math.floor of right minus left. I literally have no idea what I'm doing. Stack.push left. Left and right are the real values that are going to tell us where we are in this array. We're going left first, this would be L and R. You'd go that way by shrinking the right side of the pivot, the right side of the range. I think that's fine. Maybe once we come out here, we can create a node. Maybe we'll create a node out here. We'll call this root. new tree node, which will have no value. And you know what? We'll have another stack called the node stack. And it's going to get the value. And yeah, it's going to be like this. Okay. And then we're also going to do node stack dot push new tree node. And then once we, oh my god, I think I'm having a brain blast. Once we get outside here we can process it. We can do left. We'll destructure out of the stack dot pop. We'll have left and right. And then we'll use that to calculate another pivot. And we're just going to duplicate this line here. Once we have that pivot, we can set equal node stack dot pop. And I probably should just keep all these together, to be honest. But once we have that, we can do node stack dot node dot val equals nums sub pivot. And then we'd like to go right. This makes no sense. I'm doing anything right now. This should be the R portion. We would you know, I really feel like we were onto something with this one. Calculate the pivot. This would make more sense if I ran it in my head. This one's so convoluted though. So the node stack has one node in it, just an empty node. Give the math.floor of nums.length over 2, and let's try it with a simple one like -10, 0, and 5. Nums.length to 3 over 2 is 1.5, floor is index 1. Okay, so we're at 1. Left is 0, right equals 2. 0 is less than 2, 0 is less than 2 again, so we push onto the stack 0 and 2. And we push onto the stack a new tree node. And the pivot is going to equal, we're going to calculate a new pivot. It's going to be 2 minus 0, which is 2, over 2 is 1, plus left, which is 0, which is 2. Okay, so right is going to equal pivot minus 1, which is going to be 1. So 0 is less than or equal to 1. We're going to push on to the stack again, 0, comma, is 1. Zero, comma, 1. We're going to create another tree node, and we're going to do pivot.left of 1 minus 0, which is 1 over 2 is 0.5. Floor is 0 plus left is 0. And so we're going to get the pivot minus 1 is -1. Okay, well, now right has passed left. We're gonna pop 0 and 1 off the stack. We're gonna pop the node we created too, and we're gonna say pivot equals this is gonna be null. We don't have to actually calculate the pivot here. Node.left is going to equal node.left is going to equal nums sub left, and node.right is going to equal nums sub right. I think we're onto something. The node.val is not going to be set to anything. Maybe this shouldn't be handled here. Oh man, I really feel like I'm close or onto something, but I might have to call it. I think I'm going to have to call it. I kind of want to run it just to see what I get. I know the stack was going crazy. You see console.log node stack. Or I mean, if I don't have any data structure to print the root. Actually, yeah, if I return the root, it's just going to print the root. And actually have to comment out this. Oops, node.left.val. Actually, no, we can just do oh snap, maybe this never ends. Yep, time limit exceeded. Node equal node stack. If we push the tree node, it should probably be with nums. I feel like it should probably be with nums sub pivot. I'm gonna keep it a buck. That way the center value is already set. How do you deal with the right portion? I have no idea. And honestly, root probably even shouldn't be in here. But actually, it doesn't make sense because when I return root, still time limit exceeded. Wow, the stack isn't empty. No, I think root should be in there. So we're creating a new node based on the pivot we calculate. I kind of just wanted to return root right here, just so it ends once. My output is 0. My output is literally 0. Left and right, left and right. Oh, brother. I'm gonna try this one last time, run it in my head. while left is less than or equal to right, or stack.length does not equal 0, while left is less than or equal to right. Oh my god, I think I figured out how to go to the right. You would go to the right by pushing onto the stack if you comment this out. You could push onto the stack pivot +1 going to right. Actually, no, you want to go right now. Stack is for later. If that's the case, then you could say right equals left is going to equal to pivot plus equal 1. Yeah, this one is dead. This one is dead. I don't know how to do this iteratively. It's just too strong. I feel like we were really close. I kind of want to pull this out and run it in like a, if I could debug this or something. But yeah, I'm gonna call it here. Day 10 or 9, I can't even tell anymore. A little bit disappointing, but it is what it is. And make sure to join the Discord. Keep on grinding. The hyperbolic coding chamber never ends. And yeah, we shall return tomorrow.